Alright, today we're going to be looking at how the derivative affects the shape of a graph. So it's a little more on the conceptual side. So now that we know how to find the derivative, let's go back to what the derivative means. What does that derivative actually mean? Well, if you remember, derivative f prime of x is the same thing as dy dx, which is the change of y over the change of x, but the instantaneous. So this is the same thing as instantaneous slope, right? And if you take a look at this graph, if you take this red line right here shows that the slope at this point right here is positive, positive, positive. And as long as the slope is positive, your graph f of x, which is the blue line, is increasing. Until here, after point B, if the slope is negative, the graph in blue is now decreasing. So that's one of the things that it tells us, that if f prime, if the slope is positive, f is increasing. In the same way, if the derivative is negative, then f is decreasing. Now, the first derivative test, using this rule alone, the first derivative test can actually tell us if something about our local minimums and maximums, right? So suppose that c is a critical number, of what we call a continuous function. Remember, it has to be continuous. Then when do we have a local maximum? There is a local maximum. When do we have that local maximum? Well, this local max here at point B happens when the slope changes from positive to negative. And there has to be that switch, because pretend if it was an x cubed graph. There is no switch. The slope is positive and positive, even though the slope here at B is 0. So once again, there is a local maximum when the slope increases, the slope is positive, and then the slope changes to a negative. So when local max, when f prime of x changes from a positive to a negative. So when is there a local min? There is a local minimum in the same way, right here at point C, when the slope of the graph, f prime of x, changes from a negative to a positive. Changes from a negative to a positive. So the local max happens at point C. So it happens at the point C, right? In this case, this point, capital C, at the critical value of C. So the third and last one is like the example that I gave earlier, where if the graph was an x cubed graph, right, the slope can be 0 at that point, possibly, but if it doesn't actually make the switch, it is neither a local min nor a local max. So it is a neither min or max if f prime of x does not change sign. Does not change sign at the point C. So let's take a look at our example then. Using what we know, how do we find the local minimums and maximums of this? Essentially, it's the same thing. We're using the first derivative test right now. F prime of x is, this is f prime of x is equal to 12x cubed minus 12x squared minus 24x. I'm going to set that equal to 0 to find the critical values. This right here is to find critical values. We already know that this function is continuous because it's just a simple polynomial. I'm going to factor out the 12x here. I'm left with x squared minus x minus 2. Factor that out again. X minus 2, x plus 1. going to be equal to 0. So x here, the critical values, is going to be at 0, 2, and negative 1. Right? So the question asks, find the intervals of increasing and decreasing, where x is increasing and where x is decreasing, f of x, sorry, as well as the local mins and max. Well, in this case, we have a certain number of critical values here at negative 1, at 0, and at 2. So these are my x values, right? Well, right now, what we have here is we know the derivative values pretty easily. So if I pick the number in this interval, right, in the negative, below negative 1, so I'm going to plug in a number like negative 2. So this becomes negative. Remember, this is my derivative function here. So this value becomes negative. This will also be negative. This will be negative. So negative times a negative times a negative will become a negative. So we know that f prime of x, the output, will actually be negative, which means the slope is negative, which means my function is decreasing. At x equals negative 1, my value is 0. All of these, my slope is 0 at each of these critical values. What about at x equals negative half? This is negative, this is negative, this is now positive, meaning negative, negative, positive will now give me an output of positive. If I plug in a number between 0 and 2, like the number 1, this is positive, negative, positive. So now, multiplying those three together, you'll get a negative value. And then 3, of course, if I plug it in, positive, positive, positive will give me a positive. So what's happening here? The derivative function is telling me of something about the slope. Slope is negative, slope is 0, slope is positive. Slope is negative here, and slope is positive here, which means f of x is decreasing, increasing, decreasing, increasing here. So the intervals of increase is from increasing interval at x equals from between negative 1 and 0, as well as from 2 out to infinity. It is decreasing. F of x is decreasing from negative infinity to negative 1, as well as from 0 to 2, right? There is a local minimum at x equals negative 1 right here, right? And then there is a local maximum at x equals 0. There's another local minimum here at x equals 2 as well. Now that part was easy. Now we're going to take a look at the second derivative and what the second derivative actually tells me. So if you remember, second derivative is going to be written something like this, which is basically means it's the derivative of the derivative, right? Now this was the slope. Now this is how fast the slope is changing. So this second derivative now tells me the change in slope. Okay, the change of the slope. So for example, if I have a curve something like this, right? At this point right here, the slope is a positive value. Maybe a slope value of positive 2. Right around here, it looks like maybe a slope value of positive 1/2. Right here, slope of 0. Slope of negative 1 maybe. Down here, slope of negative 3. Now, what this tells me, what the second derivative will tell me if how my slope is changing. Now, if you take a look, this goes, the number value, the numerical value of the slope changes from 2 to 1/2 to 0 to negative 1 to negative 3. What is happening to my slope? My slope here is negative, right? The change of slope is negative. So if your second derivative is negative, as it is in this case, your it's getting flatter and flatter and flatter and going down to negative value. We actually call this curvature concave down, right? It does not hold any water. It actually dumps water. So this is if the second derivative, if the change of slope is negative, once again, if the change of slope is negative, because here the slope itself is positive, but if the change of slope is negative, then f of x is concave down, right? Therefore, in the same way, if the change of slope is positive, that's your second drawing that you have there. You go from a slope of, say, -1 to a slope of 0 to maybe a slope of 2. Now it's going from, your change is going in the positives. It's changing to bigger and bigger slope values. So if that's the case, we call this graph concave up. So once again, if the second derivative is negative, if you find the second derivative and you find it to be negative, it's concave down. If you find it to be positive, those are the intervals where it's concave up. Now take a look at this graph that you have. In the intervals from A to B, here, B to C, C to D, can you identify where it's concave up and concave down? This is what you should have gotten. Concave down from in the first interval, up, down, up, and down. So where are the points of inflection? Points of inflection are actually where the concavity changes. So point of inflection right here is where concavity must change. It has to switch values, so watch. If it goes from concave down to concave up, this point right here is a point of inflection. If it changes from concave up to concave down, this is also a point of inflection. This one goes from concave down to up, also a point of inflection. This one right here, this up at the top goes from concave up and stays concave up. This one is not a point of inflection. Concavity must change. So the second derivative must go from negative to positive or from positive to negative. Here at the point P, the second derivative is positive because it's concave up. It changes to a negative because it's concave down. This is a point of inflection. So now using the second derivative, we can actually test for the exact same thing the first derivative test asked for. The second derivative test also tests for local minimums and local maximums. And it says, suppose that f, the second derivative, is actually continuous, so the second derivative must exist and must still be continuous near the value of c. If the first derivative and the second derivative at c, you have a local minimum. So let's draw an example of a local minimum. This is a local minimum. What do we know about the first derivative at c? So the first derivative at c is the slope of the tangent line. So the first derivative must be equal to 0. Right? And the second derivative, what do we know about the second derivative at c? Well, if I have a tangent line of 0 and the second derivative is positive, then there's a local minimum. Because if the second derivative is positive, it's concave up. In the same way, if I have a local maximum, as we do here, the first derivative, what do we know about the first derivative? Sorry, I kind of missed. At c, the first derivative must be 0, and the second derivative has to be negative. Then there is a local maximum at c.